We're on complex numbers. So just at the end of the last lecture, we were thinking about the arguments of a complex number. And I'd like to keep going from there a little bit. So sort of thinking about Cartesian coordinates, polar coordinates. And it's really important that it's convenient to pass between the two of those. So here is a useful thought. So we can pass between Cartesian and polar coordinates. So here's my kind of picture of what I'm doing. So this is my Argand diagram, my complex plane. Here is some little complex number, which I might think of as having Cartesian coordinates a comma b, or I might think of as having modulus r and argument theta. And I'd like to know, if I know a and b, can I find r and theta? If I know r and theta, can I find a and b? That's the kind of point here. So if z, which is a plus bi, has modulus r and argument theta, then we can find a and b. So maybe I'll draw this on here in another color for you. So this is just a little bit of trigonometry. So this bit is r cos theta, this is a, this is b sine theta, sorry, r sine theta. Let's try that again, which is b. So a is r cos theta, and b is r sine theta. So one kind of way of thinking about z then is to think of it as being r times cos theta plus I sine theta, which is a representation that we find coming up in various contexts. In the other direction, if z is a plus bi, and I want to find r and theta, well, we know how to find r just by the definition. So r is the modulus of z. It's just defined to square root of a squared plus b squared. That's how we defined it. And also, again, looking at the diagram, tan theta is b over a, at least in the case when a is not 0. I'm very scared about the possibility of dividing by 0. I don't want to risk it. But as long as a is not 0, then b over a is going to give me tan theta. And from that, I can kind of recover theta. But as we know, there's this sort of ambiguity about what theta is, because if you have some argument theta, well, theta plus 2 pi or theta plus any integer multiple of 2 pi will also be a valid thing. And that's reflected in the fact that there's not a kind of unique inverse here. So I'll just put determining theta is delicate. So in practice, this is not a problem. You just need to kind of have your wits about you a little bit. So I want to know what happens when we multiply. We saw that we could interpret addition of complex numbers geometrically with that kind of vector addition parallelogram diagram. What happens with multiplication? Well, we know what happens to the modulus when we multiply. That behaves nicely. What happens with the argument? So this is proposition 5. And this says take z and w in the complex numbers but not 0, then, so remember the argument of 0 isn't defined, so I want to ignore that. The argument of z times w is equal to the argument of z plus the argument of w. So a couple of little comments here. One is that here we're working with arguments modulo 2 pi, so this idea that these two are equal up to some multiple, integer multiple of 2 pi. So it's important that we remember that. So this is working with arguments modulo 2 pi. The other is that you've seen this kind of relationship before. This looks a bit like a logarithm, right? That's not a coincidence. There are no coincidences in mathematics. So maybe I'll just note here, this looks a bit like log. Looks like log. That's very pleasingly alliterative. So let's think about how we're going to prove this. So this is not too bad, actually, given this kind of thinking that we've been doing up here. So if I let theta be the argument of z and phi be the argument of w, I hope you're making good progress with learning the Greek alphabet. I'm not fantastic with every Greek letter, but theta and phi are really good Greek letters to know. So then what we've just said is that z is going to be the modulus of z times cos theta plus I sine theta, and w is going to be the modulus of w times cos phi plus I sine phi. So we can just multiply. So zw is the modulus of z times the modulus of w times cos theta plus I sine theta times cos phi plus I sine phi. And I can do some tidying up here. So one thing is that I know what happens with this multiplication for the modulus. So that's the modulus of zw. I'll write it that way round. And I guess we're using proposition 3 here. I'm not going to record every time you use proposition 3 for the rest of all time, because it's just going to come up so much. But I'll just note it here to remind you. And if I multiply out here, I get cos theta cos phi minus sine theta sine phi. That's coming from these terms, plus I times cos theta sine phi plus sine theta cos phi. And hopefully you might recognize these from your kind of compound angle formulae in trig. So this is the modulus of zw times cos of theta plus phi plus I times theta plus phi. And so we can read off immediately that the argument of zw is theta plus phi, which is the argument of z plus the argument of w. Of course, it's not a coincidence that the trig here works out nicely, right? So we can use this to make sense of multiplication in a geometric way. So remark, we can interpret multiplication in C geometrically. So multiplying by a non-zero complex number z. Multiplying by 0 is not so exciting. Multiplying by some non-zero complex number z, that rotates the complex plane. I'll move over here. Anti-clockwise by the argument of z. This is a consequence of that proposition we just proved, and it enlarges by factor the modulus of z, and that's all centered on the origin. So there is a nice way to make sense of multiplication with our geometric view of complex numbers as well as algebraically. So we're going to find ourselves using this proposition lots. OK, I want to introduce you to some particularly nice complex numbers. They're called the unit circle. So definition, the unit circle in C, and I'm defining unit circle, is kind of what you expect. But I'm also telling you this because I want to tell you that it gets called S1. And S1 is defined to be the set of all z in C such that the modulus of z is equal to 1. So geometrically, it's a circle of radius 1 centered on the origin. And what we've just noticed is that we can write that in another way. So here are a few little remarks about the unit circle. So we've just seen, essentially, that S1 is also the set of all cos theta plus I sine theta, where theta is real. So that would be another way of thinking about it. Here is an amusing and really surprisingly useful fact about numbers in the unit circle. So if I take z in S1, what is the inverse of z? Well, we know that z times z bar is the modulus of z squared. If you're in the unit circle, the modulus of z squared is 1, so z times z bar is 1 in this case. So the inverse of z is its complex conjugate. Cute, also useful. And this is also going to lie in the unit circle. So the unit circle has all sorts of nice structure within itself. And in fact, S1 is a group under multiplication. This is not the time to tell you what a group is. There's a course on that. It's called groups. So in February, some person will introduce you to groups in the course on groups and group actions, and you'll meet at S1 as an example. So this thing about the inverse is relevant. There are some other things that go into that. The thing to remember here is the unit circle is a kind of important and interesting object. It has kind of structure. So here is a really super exciting result about numbers in the unit circle. This is a theorem, and it's called de Moivre's theorem. And this is going to be, I imagine, familiar to quite a few of you, but I might not be phrasing it necessarily in the way that you're used to. So for z in the unit circle and any integer n, remember this just means n is any integer, we have that the argument of z to the n is n times the argument of z. So this proposition is a very special it's kind of related to this. We're going to be using this proposition to feed into it, but this is kind of helpful. So you might be more familiar with the equivalent formulation. Equivalently, for theta in R and n in Z, we have that cos theta plus I sine theta to the power n is cos of n theta plus I sine of n theta. So definitely when I first learned about de Moivre's theorem, I learned about it in this form, but this form is a really helpful way of thinking about it. So I encourage you to think about why these are saying the same thing, because if you understand why they're saying the same thing, that's a really good way, kind of sign that you are understanding the theorem. So let's prove this. So I'm going to fix some z in S1 and show that the theorem applies to this z. And for n greater than or equal to 0, so for non-negative n, I'm going to use induction on n. And I'm going to write that down because it helps the reader to know that we're going to use induction. So for n greater than or equal to 0, we use induction on n. So my base case is n is 0, and that's just a quick check. So z to the 0 is equal to 1. So the argument of z to the 0 is n times the argument of z in this case. So that was important, although not super exciting. More interestingly, let's think about the inductive step. So let's suppose the result holds. For some n greater than or equal to 0. So we've got some fixed value of n where we're supposing it holds. So we're saying that the argument of z to the n is equal to n times the argument of z. And now we want to think about the argument of z to the n plus 1. So let's do that over here. So then the argument of z to the n plus 1, I want to relate to the argument of z, but I can do that using proposition 5, which tells us that that's the argument of z to the n plus the argument of z. So I'll write down that's by proposition 5. And then we know about the argument of z to the n because that was our induction hypothesis. So this is n times the argument of z plus the argument of z by the induction hypothesis. And that's equal to, of course, n plus 1 times the argument of z. So we've shown that the result holds for n plus 1. So that's an inductive proof that shows us that this relationship works for n greater than or equal to 0. Now I want to think about negative n. And one possibility would try to be to do a kind of induction downwards. That can be a useful strategy. But actually, I think we can just use the result for positive values. So for n less than 0, we use the result for positive n. So this can be a nice strategy to kind of use work you've already done to save yourself a bit of effort. So if I fix some negative n, I'm going to let m be minus n. So of course, m is then positive. So by our previous result, so we know that the argument of w to the m is m times the argument of w for any w in S1. That's using the result for m, which is a positive value, so that follows from our previous part. So we just need to think about how we're going to apply this. Well, let's think about z to the n. Z to the n is z inverse to the power m. That would be another way of rewriting it. And z inverse, I noted in my kind of fun fact over there, was the complex conjugate of z. So we're going to be able to apply this result with w being the complex conjugate of z. I'd quite like to know what the argument of the complex conjugate of z is. But if you ponder that for a moment, you'll see that it's minus the argument of z. Again, everything is modulo 2 pi here. So the argument of z to the n is the argument of z bar to the m, which is m times the argument of z bar, which is m times minus the argument of z, which is n times the argument of z. So that proves the result for negative values using the result for positive values. So Tomarov's theorem is just kind of somehow utterly fundamental, and it gets used lots. Here is a specific example of a kind of classic way in which it gets used, namely trig compound angle formulae. So by Tomarov, for any theta in R, we know that cos of 3 theta plus I sine of 3 theta is cos theta plus I sine theta cubed. That's from that kind of equivalent formulation. My goal here is to find some nice formula for cos of 3 theta in terms of cos theta, for sine of 3 theta in terms of sine theta. So I'm going to expand this out. So this is a binomial theorem and kind of tidying up. And I think I'm going to get cos cubed theta minus 3 cos theta sine squared theta plus I times 3 cos squared theta sine theta minus sine cubed theta. So that's just by multiplying out. I've had quite a lot of practice at multiplying out cubes, and I'm just trying to tidy up the real and imaginary parts as I go along. So comparing real and imaginary parts, gives that cos of 3 theta is cos cubed theta minus 3 cos theta sine squared theta. And then I got a formula for sine squared theta in terms of cos theta, right? So I could kind of keep going and tidy up, and I could write out some kind of corresponding formula for sine 3 theta, and again, tidy that up. So I'm going to let you do that tidying up while we have a short pause. I also have one other thing for you to do in this short pause. At the end of each of your lecture courses this year, we'll give you a paper questionnaire towards the end of the course so that you can give some feedback on how you found the course, how you found the lectures, and so on, so that we can then, as a department, use that to improve teaching for next year. Even though it's only Thursday of week 1, this is in fact the last lecture of this course, officially, which means it's questionnaire time. So I'm going to put some piles of these in strategic places. If you could pass them along so everybody gets a questionnaire, that would be great. If you want to fill it in during the lecture, you can. And if you just leave 2 piles, one at the top there and one at the top there, I'll collect them at the end. If you prefer to fill it in later, you can also return it directly to the academic admin team, who are the people who process them. So this is your opportunity to give some feedback on the very short complex numbers course. Okay, the questionnaires are making their way round. So if you can concentrate on keeping the momentum going, passing those around, that would be great, so that everybody gets them. I will try to remember in a couple of minutes to check that everybody's got them. But hopefully that's given you a little bit of a chance to think about these trig formulae, especially if this isn't something that you've thought about before. Let's keep going over here. Because, excitingly, it's time for nth roots of unity. So here's a definition. So if z is a complex number, n is a strictly positive integer, which you might call a natural number, but somehow we can't decide whether or not 0 is a natural number, and I don't want to have an argument about it, so I'm just trying to be unambiguous, and z to the n is equal to 1, then we say that z is a root of unity. Or, more precisely, an nth root of unity. When I learnt about this stuff, I think I remember kind of thinking, oh, roots of unity, that sounds really cool. And then unity turned out to be 1, and it's sort of slightly less dramatic than I expected. But roots of 1 are still pretty good. There are lots of interesting things to explore. For example, proposition 7 tells us which numbers are in fact roots of unity. So we can pinpoint where these things are without too much difficulty. So let's take z in C. Then z is an nth root of unity if and only if. And I've got 2 conditions here, one on the modulus of z and one on the arguments of z. So I need the modulus of z to be 1 and the argument of z to be 2k pi over n for some integer k. So this precisely describes what the nth roots of unity look like. So let's prove proposition 7. And you'll notice that proposition 7 is an if and only if statement, so it's really 2 statements packaged as one. Let's prove the 2 separately and try to help you see which one we're doing. I find it helpful to write these little kind of implication arrows and brackets. When I'm doing this for my own benefit, I do this not just for you. So we're going to do the left to right first. So we're going to suppose z is an nth root of unity. So we're supposing that z to the n is equal to 1. And then we want to deduce kind of interesting things. Well, we can say something about the modulus straight away. The modulus of z to the power n is the modulus of z to the n is 1. And the modulus of z is strictly positive. So the modulus of z had better be equal to 1. So modulus of z is just a real number here. And by de Moivre, which conveniently we've just proved, and comma by de Moivre, comma, the argument of z to the n is n times the argument of z, but we know that z to the n is equal to 1. So the argument of z is the argument of 1 over n. And now we have to concentrate because there's a little subtlety here because we're working with arguments modulo 2 pi. So it'd be tempted to say the argument of 1 is 0, therefore this is 0, and that wouldn't be correct. All we know is that the argument is 0 plus an integer multiple of 2 pi. So all we know is that this is 2k pi over n for some integer k. And that gives us what we were looking for. The other direction, let's get rid of these smudges for you. The other direction, so now we're going to suppose that the modulus of z is equal to 1 and the argument of z is 2k pi over n for some integer k. So then what can we say about the modulus of z to the n? Well, that's the modulus of z to the n is 1. We like modulus. Modulus works out really nicely. And also, the argument of z to the n is n times the argument of z is 2k pi. So what's that telling us? It's telling us that z to the n has the same modulus and argument as 1. So in fact, z to the n is equal to 1, so z is an nth root of unity. And that finishes our proof. So if I carry on over here, so one small observation from proposition 7. So remark, proposition 7 shows that roots of unity lie in S1. They lie in the unit circle. And that's a kind of handy thing to be aware of occasionally. Right, how are we doing on questionnaires? Can you please put your hand up if you do not have a questionnaire? Interesting. Could you please put your hand up if you have some spare questionnaires? OK. The people who didn't have questionnaires were over here somewhere. Oh, thank you. More questionnaires. Wave if you need a questionnaire. OK, so I'm going to send some this way and some this way. And it would be great if you could sort them out amongst yourselves. And hopefully there are enough. So, cute consequence of proposition 7 is that we can count nth roots of unity. So I think maybe I said on Monday, a corollary is a quick consequence of something you've already proved. So corollary 8 says for n greater than or equal to 1, there are exactly n nth roots of unity. And that's quick to prove from proposition 7 because we know what the nth roots of unity are. So by proposition 7, the nth roots of unity are, so one way of writing them would be as cos of 2k pi over n plus I sine of 2k pi over n for any k in the integers. That makes it look like there are lots of them, but of course there's lots of duplication here. So there are n such distinct values, e.g. we could choose k to come from 0, 1, up to n minus 1. So that was a handy consequence. It's good to know not only where the nth roots of unity are, but that we've got n nth roots of unity. That's a good thing to know. There are some nth roots of unity that are even more exciting than others. There are some nth roots of unity that are nth roots of unity, but aren't smaller roots of unity, aren't nth roots of unity for smaller m. And they're particularly important, so they get a special name. So this is a definition. So let z be an nth root of unity if z to the m is not equal to 1 for 1 less than or equal to m less than or equal to n minus 1, then we say that z is a primitive nth root of unity. And these kind of have connections with things from group theory and other things that you will see. That was a very strange noise. Other things that you will see this year. So a primitive nth root of unity is like n is the first power of z where you get 1. So here is a proposition that is useful and certainly applies to primitive roots of unity, although it applies a little bit more generally than that as well. So if z is an nth root of unity for some n greater than or equal to 2, and z is not equal to 1, then z to the power n minus 1 plus z to the power n minus 2 plus dot 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 plus z plus 1 is equal to 0. This is the kind of thing where if I were working on these lecture notes this afternoon thinking about them, I'd be thinking, oh, why has Vicky excluded the case when n equals 1? What was special about that? That kind of, why are the hypotheses there? That's the sort of question that you can be asking yourselves. So this is not too tricky to prove because we know that 0 is z to the n minus 1. We're assuming that z is an nth root of unity. And we can factorize z to the n minus 1. If this factorization is not second nature to you, I invite you to think about it because it's a really useful factorization. It kind of generalizes difference of two squares. And in fact, it's this. And z is not equal to 1. And that's the end of the proof. So this is not super difficult, but it's kind of useful. It's a nice result. So this starts to have some nice consequences geometrically, for example, when you're thinking about roots of unity. OK. I want to think about another way to represent complex numbers. We've sort of thought about modulus argument, and we've thought about this Cartesian coordinates kind of way. There's another very useful way of writing them, which comes from the following fact, which gets called Euler's formula, at least sometimes. And this says, for theta in R, we have e to the I theta is equal to cos theta plus I sine theta. While you take 10 seconds to just absorb how lovely that is, how are we doing with questionnaires? Please put your hand up if you do not have a questionnaire. Result. Very good. Now, you will notice that I have labeled this as fact rather than theorem or any of those kinds of things. This looks a lot like a thing that needs proving, right? And it does need proving. But in order to prove it, we first need to have defined the exponential and the cosine and the sine. And since we haven't done any of those things, we're not in a very good place to prove this. Defining the exponential is something you will do in analysis this year, and also cosine and sine, once you've learned how to add up infinitely many things in a safe, controlled manner. It's very important to be careful when adding up infinitely many things. Once you have kind of got your license that you are safe to do that, you can think about the exponential, and then you'll be able to think about why this is true. So I just put a little bit more in the online notes. So if you want to kind of read a little bit more about that, have a look at the online notes. But we're just going to kind of accept this as a fact for our purposes. So here is a remark. This gives a very convenient way to represent a complex number. So if z has the modulus of z is r and the argument of z is theta, then z is r e to the I theta. When I started learning about complex numbers, I definitely thought about them most in that a plus b I form. And then I think when I was doing A-level kind of studying a bit further, I thought about them more in the r times cos theta plus I sine theta form. And I probably think about them more in this form now. So I want to stress that this is very convenient, so I'm going to put flashing neon lights to remind you. So if this is relatively new, it feels a little bit uncomfortable. It feels natural to go back to your old ways of thinking about it. That's what we do when we meet something new, is kind of try to see, well, can we keep going with the old way? This has lots of advantages. I really encourage you to look for opportunities to practice working with this way of thinking about it so you become more fluent. For example, proposition 10. So proposition 10 says, take z, a non-zero complex number, and you'll see why I want it to be non-zero. Z in C, but not 0. That's a 0. Then Z has exactly n nth roots. So for any n greater than or equal to 1. So we thought about roots of 1, right? Corollary 8, said there are exactly n nth roots of 1. This is generalizing to there are exactly n nth roots of any non-zero complex number, which is kind of nice. So let's prove this. So I'm going to do this in 3 parts, and I'm going to kind of bullet point what the sections are to try to help you see what the structure is clearly. So the first part is that there's at least one nth root. Right? At the start, it's not completely clear that there is at least one nth root. So if I let R be the modulus of Z and theta be the argument of Z, so Z is R e to the I theta, I can sort of stare at Z in this form and guess what an nth root might be. So there is a, in fact, unique positive real S such that S to the power n is equal to R. So this is since R is greater than 0. How do we know this is true? By analysis. So I'll just put C prelims analysis. You will think about why you can do this in that course. So that's going to be the modulus of my proposed root. And now I'm going to let phi equal theta over n. Where did I start over here? Yeah, that's OK. So if I let w be equal to s e to the I phi, then w to the n, when you do a quick calculation, you see is equal to z. So there's definitely at least one root. Now I'd like to show that there are, in fact, at least n nth roots. How do you show that there are exactly n of something? You show there are at least n of something. You show there are at most n of something. That could be a useful strategy. So I want to show that there are at least n roots. So I'm going to take w as above. So w is a fixed nth root. I can get a whole bunch more nth roots by multiplying by an nth root of 1. So if I let alpha be an nth root of unity, then you do a quick calculation and you realize that alpha times w to the power n is also equal to z. So alpha w is another root of z. And by corollary 8, there are n such alpha, giving, well, at least n distinct nth roots of z. So this says I can think of n distinct nth roots of z. We haven't shown that there aren't some more. Maybe there's some more that have some other form. Of course there aren't. That's what we're about to prove. But that's why we're kind of structuring it like this. So if I carry on over here for the third bullet point, the third bullet says at most n nth roots. So if I again take w as above, so w is my fixed nth root of z, I want to show that any nth root of z must be a root of 1 times w. That would do it. So if I let u be an nth root of z, then my secret aim, if you like, is to show that u must be w times some root of nth root of unity. Well, we know that w to the n is z, and that's also u to the n. That wasn't a very good n. Let me try again. And z is not 0, so w is not 0. So I can do u divided by w to the power n, and that's now 1. right? Having got u to the n and w to the n are the same, if I just rearrange, this says that u over w is an nth root of 1. And by corollary 8, there are n of these. So there are at most n choices of u. So that completes the proof. So it's a little bit fiddly, and you might want to kind of think about that in your own time, but hopefully the structure at least makes some kind of sense. So that was thinking about roots of a particular complex number, and that means that we've sort of thought about solutions to the polynomial equation w to the n equals z. We've just counted solutions to that equation. We'd like to know about solutions to polynomials more generally. I said on Monday we could think about solutions to quadratics, and we'd like to be able to generalize, and that's what we're going to do now. So the first thing is to show that if you've got a polynomial with complex coefficients, a complex polynomial of degree n, then it can't have too many roots. So this is proposition 11. And this says a complex polynomial, meaning a polynomial with complex coefficients of degree n, has at most n roots. I mean, maybe it has no roots, maybe it has some roots. I'm not making any claims about that in this proposition. All I'm saying is there are at most n complex roots. So I mean n roots in C. So let's prove this. And my strategy is going to be to use induction on n, the degree of the polynomial. So n is 1, for example, as a base case. That's a quick check. I'll let you make sure that you're happy to see that a linear polynomial with complex coefficients has at most one root. I feel confident that you can handle that. So let's do the inductive step. So I'm going to let P be a complex polynomial with degree n, and I'm going to suppose the result holds for polynomials with degree less than or equal to n minus 1. That's our inductive hypothesis. So I want to show that the number of roots of P can't be too big. Dividing through by the leading coefficient, the coefficient of z to the n, if you like, by the leading coefficient, x to the n maybe, doesn't change the roots. And what that means is that we may assume that P is a monic polynomial. Monic means it has leading coefficient 1. So P looks like P of x is x to the n. It has leading coefficient 1 because it's monic. Plus a n minus 1 x to the n minus 1 plus dot 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 plus a1x plus a0 for some a0, a1, dot dot dot, a n minus 1 in C. I would like you to notice two things about this. One is that I've very carefully introduced what a0 up to an minus 1 are. If you turn up at a party and you take your friend along and they don't know the people there, you introduce them, right? It's really rude not to, because otherwise people can't have a kind of sensible conversation. We can't talk about these things without knowing what they are. Also, notice how I've carefully matched the coefficient with the power so that it's dead easy to do. I didn't want to start with a0 or a1 here, right? This is a top tip. This will make your life easier. If P has no roots, then we're done. If P has a root, say alpha in C, then P of x is equal to x minus alpha times f of x for some complex monic polynomial f with degree n minus 1. If you haven't seen how to prove this, or you're not, more to the point, you're not confident you could do it yourself, I did put the details in the online notes. So if you want to think about that, you can. What this tells us is that any root of P is either alpha or a root of f. So by the inductive hypothesis, f has at most n minus 1 roots, and any root of P is alpha or a root of f. So P has at most, okay, I need to carry on over here. P has at most n roots. And that completes the induction argument. So proving that a complex polynomial of degree n has at most n roots is not too difficult. I mean, I've gone through that fairly swiftly. You're going to want to look at that in your own time, but it's very doable. What we'd really like to know is, does it have any roots? Does it always have at least one root? Does it always have n roots? And the answer is given by theorem 12, which is super important, and is called the fundamental theorem of algebra. You should draw some conclusions about the importance of this theorem from the fact that it's called the fundamental theorem of algebra. And this says any complex polynomial of degree n has exactly n roots counted with multiplicity. So repeated roots, you have to count the appropriate number of times, which, when you sort of think about it, is a relatively natural thing to do. So that is, if P is, well, we may as well focus on a monic complex polynomial with degree n, then we can factorize P of x is x minus alpha 1 up to x minus alpha n for some alpha 1 up to alpha n in C that don't have to be distinct. This theorem takes quite a bit more work to prove than proposition 11. It's not in this course. You're going to want some extra ideas, so maybe some ideas from complex analysis or topology. So you will see proofs of this theorem in the next couple of years that you can be looking out for. For now, you may assume this theorem, but only if you really, really have to, right? If you can avoid this theorem, you want to avoid it because you haven't seen a proof. And that means you're sort of not morally on top of this theorem. So if you possibly can, avoid using this theorem, but know that it's there if you need it. The history of this theorem is really interesting, and I put some links to where you can read a bit of an introduction to that on the online notes. that is the end of the complex numbers course. On Monday, excitingly, we will be here for linear algebra. If you want to leave your questionnaires at the top on that side or that side, I will collect them up. Otherwise, please return to academic admin. See you on Monday.